This is Lecture 8 on percentiles and position. This is a little bit of a mashup lecture. We've been talking about various parameters for numerical variable, such as mean, median, and standard deviation. We will learn a few new parameters here, roughly where mean and standard deviation give you a pretty good description of a symmetric numerical variable. We're going to learn some analog things for a very skewed distribution, but we're also going to learn two ways of describing the position of an individual in the population or sample, or more precisely, the position of that individual's value of a certain numerical variable among all the other values. We'll begin with the notion of percentile. You are familiar with percentile, at the very least when you opened up your SATs, you got to see what your percentile was. But let's say this a little bit more precisely. The 95th percentile of a data set is the data value such that 95% of the data is less than or equal to it, and therefore 5% is greater than it. Likewise, the 20th percentile is the data value such that 20% of the data is less than or equal to it, or more generally, the pth percentile is the data value such that p% of the data is less than or equal to it. So, turning that around, you can ask what percentile is any particular data point. In particular, as I said, when you opened up your SATs, they told you not only your score, which is a little hard to tell what that means, particularly if you're not used to the SATs, but they told you your percentile. If they told you you scored in the 90th percentile, you knew that 90% of people did worse than you, 10% did better. Notice there's a little ambiguity about what about the people that did exactly the same. How that is handled depends on who's doing it. Excel follows one convention. Various books follow different conventions. It's in no way specified, and we're going to sweep that under the rug and just do what Excel does when it comes time to compute. Anyway, you've already seen a percentile. You've seen the median. The median is nothing but the 50th percentile, because 50% of the data is less, 50% is more. Two other percentiles that are talked about frequently enough to get their own name is the first quartile, or Q1, which is the 25th percentile. Of course, it's called a quartile because a quarter of the data is less than it. The third quartile, or Q3, is the 75th percentile. And this begs the question, what's the second quartile? But of course you know that, right? The second quartile is just another way of talking about the median, because it would be the 50th percentile. People often talk about the difference between Q3 and Q1. The third quartile minus the first quartile is called the interquartile range, which is a mouthful, so it's usually written IQR. It tells you the range of the middle 50% of the data, right? Half the data falls between those 2 points, the middleest half, whatever that means. It's a pretty good measure of how spread out data is. So just like the mean and the standard deviation tell you the middle and the spread, so it gives you a good picture of symmetric data, the median and the interquartile range are somewhat analogous for the skewed data. These five numbers, the minimum of a data set, which is the lowest value, of course, Q1, the 25th percentile, the median, Q3, and max, the maximum value. Those five numbers are called the five-number summary, and they divide the data into quarters and give you a nice picture of what's going on. What do I mean? Well, suppose I handed back a test, you got, say, a 90 on it, you want to know how you did. If, that's the best score in the class, you're a lot happier than if 2/3 of the class got better than a 90. So I could give you the five-number summary. I could tell you that the lowest grade in the class was 37, the 25th percentile was 70, the median grade was 82, and the 75th percentile was 88, and finally the maximum was 99. Parenthetically, Of course, I would not tell you the minimum and the maximum because they're individuals' grades and could be potentially embarrassing. But I usually will, when I hand back grades, give you the middle three and let you kind of guess about the min and max. So how would that tell you how people did on the score? Well, you'd know that 1/4 of the class got between 37 and 70. The next quarter of the class, that would be the worst quarter of the class, the next quarter of the class got between 70 and 82. The third quarter of the class got between 82 and 88, and the highest scoring 25% got between 88 and 99. So your grade of 90, better than the 75th percentile, better than 75, maybe 80% of the class, but not much better than that. So that gives you a pretty precise notion of where you fit in the class. That 5-number summary is such a good description, particularly for skewed data, that it is often assembled into an absolutely beautiful graphical representation called the box plot. It was, I don't think invented, but popularized by John Tukey, who was a famous 20th century statistician. He was a big proponent of exploratory data analysis. What does that mean? That means looking at data and searching for patterns. Later in the semester, we'll do inferential analysis, where we start with a pattern in mind and decide if we have good evidence from the data that it's there. This is a much more informal, much more creative process where you just try and see what kind of patterns you see. For that kind of creative process, it's nice to have a really quick, simple, visual picture of the data, and that's what the box plot gives you. Here's how it works. Like histogram, dot plot, all our other visual representations, it begins with a number line, a horizontal number line, that includes everything from the minimum to the maximum. It can go beyond those, as always. So from 37 to 99 is on this number line. And then the first step, or second step, I guess, is to draw a little rectangle that goes from Q1 to Q3. So these red lines here at 70 and at 88 are the first and third quartile, and we connect those lines to make a rectangle. Right? As always, the x-axis is values of the variable. So 70 and 88 are values of the variable. They're specific percentiles. Next, inside that box, we draw a vertical line at the median. One thing you can see already is that if we were sort of making a dot plot here, a quarter of the x's would go inside the box to the left of the red line, and a quarter would go inside the box to the right of the red line. So they're going to be a lot more scrunched on the right. The data is more densely packed on the right. It already gives you kind of a sense of what the shape of this distribution is. Finally, we draw a horizontal line from Q3 all the way up to the max, in this case 99, and from Q1 all the way down to the min at 37, and usually we draw short vertical lines to sort of cap it off. That's the box plot. It's also sometimes called box and whiskers plot, which I don't like because the image of my whiskers looking like this is unsettling to me. And you can see, I hope, that already you know something about the shape of the histogram. In fact, I'm going to pause and let you think about, you pause the tape and let you think about how you would describe the shape of the histogram that this data probably represents. Well, it's probably skewed left, right? Because this long tail to the left corresponds in a histogram to pretty much the long tail to the left. In fact, in general, these horizontal lines capture roughly what you think of as the tail of the distribution, and this central rectangle, the middle peak. You can see there's a long left tail and a short right tail, and even more precisely, you can see that within the peak, the data is more clumped to the right than the left, giving even more of a sense of left skewed. That's the box plot. Very useful, for instance, when you're comparing a lot of data sets. If I made a box plot of each quiz over the semester, I could quickly see trends like the median's getting better, the variation is getting less, Things like that would leap out at me. All right, we will not spend much time on the box plot. We will not do much exploratory data analysis, sadly, but I wanted you to see it and have some sense of what it tells you. Now I want to shift gears a little. The percentile in itself describes the position of a data set. When you have your score and I tell you your percentile, I've told you where you fit in the data. That's helpful. There's a second way to describe where an individual fits in the data that's better suited to the kind of symmetric unimodal data we will usually look at. It's called the z-score. The z-score is something you can compute for an individual data point, that is, for an individual in your population or sample. How do you compute it? With this formula, what it tells you is the number of standard deviations above or below the mean your data value is. The formula is z equals x minus mu over sigma. That is, you take the value of your data point, you subtract the mean, and you divide by the standard deviation. Since I've written mu and sigma here, you understand that we're in a population context, but you can just as well do this in a sample context, where you would write x bar and s. Hopefully, an example will make this clearer. I'll remind you, as we've said before, women's heights are roughly bell-shaped, and they have a mean of about 65.5 inches and a standard deviation of 2.5 inches. So I could ask, what would the z-score of a woman whose height is 69 inches be? To find that, you would take the height of 69 inches, and you'd subtract the mean of 65.5 inches. That gives you 3.5 inches. That's how far above the mean this particular woman's height is. It's 3.5 inches above the mean. But now, to scale that, to express it in units of standard deviation, we divide by the standard deviation. 3.5 divided by the standard deviation of 2.5 is 1.4. So that tells us that this woman's height is 1.4 standard deviations above the mean. Let me have you do two examples. So first, what would the z-score of a woman who is 60.5 inches tall be? Pause the video, work this out, we'll go over it, and then we can do the second example. Okay, 60.5, her height, minus 65.5, the mean gives you negative 5. You divide negative 5 by 2.5 and you get negative 2, and you conclude that she is 2 standard deviations below the mean. Below because it's negative. All right, if you've got that, try this. Let's find the z-score of a woman who's 72 inches tall. Okay, 72 minus 65.5 is 6.5. If you divide that by 2.5, you get 2.6, and you conclude she is 2.6 standard deviations above the mean. Why do you care? The z-score tells you something very important about how surprising a data point is. Why is that? That is what the z-score tells you when you combine it with the empirical rule. You probably already recognized we're using the same language as we used in the empirical rule in lecture 5, I believe. And let me remind you of the empirical rule. The empirical rule tells you that in a reasonably bell-shaped distribution, symmetric and fairly unimodal, about 2/3 of the data falls within 1 standard deviation of the mean. About 95% of the data falls within 2 standard deviations of the mean, and almost all of the data falls within 3 standard deviations of the mean. These more precise numbers are associated with a specific distribution that's considered the standard bell-shaped distribution, which we'll get to in a bit. The point here is, because the empirical rule is talking about how many standard deviations above and below the mean you are, it's really talking about your z-score. So we can reformulate the empirical rule as saying, for a symmetric, reasonably unimodal distribution, 2/3 of the data has z-scores between -1 and 1. 95% have z-scores between -2 and 2, and 99% have z-scores between -3 and 3. That's a statement that has nothing to do with the units of the variable you're using. It's universally true as long as the data is symmetric and unimodal. What does that mean? That means that no matter what, about 2/3 of the data has a z-score between -1 and 1, so that would be typical. It's a woman who's not particularly tall or not particularly short. The middle 2/3 of all women have z-scores in that range. 95% have z-scores between -2 and 2. So 19 out of 20 women have a z-score between -2 and 2. Everybody in this class, although I'm obviously not looking at a class right now, but everybody but 1 or 2 people has a height in that range. That's the usual range. And on the other hand, a z-score above 2 or below -2 is unusual. Each of those happens maybe 2.5% of the time. Quite rarely. And a z-score over 3 or under 3 is something that happens 1 time out of 1,000, and it's shocking. So to make this as concrete as possible, if you're walking down the hallway and you see a woman whose height has a z-score between -1 and 1, you would describe her as average height. You might be able to say, she's slightly above average or slightly below average, but she's pretty much average. If you see a woman who's, say, got a z-score between 1 and 2, you'd probably call her tall, but not unusual. You saw a woman whose z-score was between 2 and 3, you would say she's tall. Unambiguously, that would probably be the first thing you'd think about when you see her. She's as tall as 1 woman out of 40. If you see a woman whose height has a z-score greater than 3, you would probably take out your cell phone and call your mom and say, I just saw the tallest woman ever. You may never in your life have seen a person whose height has a z-score above 3 or below -3 in person. If you have, you haven't seen many. The important thing here, though, is that this isn't about height. All of that could apply equally well to IQ scores. Somebody whose IQ is more than 3 standard deviations above the mean is just as shocking as someone whose height is, in a different context. Any variable that's reasonably symmetric and unimodal, the same conditions apply to. It gives you a universal way of identifying things as unusual or shocking, essentially identifying outliers. Sometimes people define an outlier to be something that's more than 2 or more than 3 standard deviations from the mean. Again, I don't like that. It depends on your context, but it does give you a way of identifying how unusual something is. And if you recall when we talked about outliers, what is important about identifying something as unusual is recognizing that it has a story attached and that you should be looking for that story. Later in the semester, we will be talking about distributions. We will know their mean and standard deviation and know they're symmetric, and I'll give you a data value. And I'll say, is this surprising? And one way of answering that is to look at its z-score. And if you see that its z-score is 20, you can say, yes, that's really surprising. In particular, it's a little hard to believe that it could have come from this data set. Probably there's something messing things up, confusing you, making it come from the wrong data set, changing the conditions. There's some story there that should be figured out. All right, let's stop here, and let me just tell you what it is you should be able to do right now. First off, you should be able to interpret and use quartiles in the interquartile range. Just know how they're used, what they're telling you. Likewise, you should be able to interpret box plots and relate them to the shape of the histogram. We will not be making box plots, But I might show you a box plot and ask you, did this histogram, did this come from a skewed right distribution or a skewed left distribution? Does this have long tails or short tails? You should, we've pretty much said this before, know when to use mean, standard deviation, and z-scores. All of those things are in the symmetric, reasonably unimodal context, versus when it makes more sense to talk about medians, quartiles, and percentiles. Usually that's best when you're looking at skewed data. And now, after we've looked at this for a while, you should be able, first of all, to use z-scores to give a universal picture of the place of a data value in a data set. You should recognize, the z-score will tell me if this is a surprising value. And finally, we will learn in class how to compute percentiles, quartiles, and z-scores in Excel. Of course, you can compute z-scores by hand. We've seen that, and that's pretty easy. It's actually a little bit tricky to get exact values for percentiles and quartiles. We will always do that by Excel.